Alright, so far we have been looking at structs as a way of collecting related data together into a single location, right? And obviously that would, in order to make that useful, I should be able to sort of pass that struct directly into another function and sort of use function calls that involve structs, maybe also return structs as the return type of functions and so on, right? And yes, sure enough, that's actually possible, right? So let's look at this code out here. What I have got is that I have declared a struct fruit apples, and I am using the typecasting and so on. This was not strictly required out here because after all I am anyway declaring it as a struct fruit, but there is no harm, it is definitely correct to do this. And now what I am doing is I am actually calling a function print underscore info and passing the struct directly as a parameter into the function. So let us go look at the definition of the function. As with C, right, basically I need to have that function defined before, or I at least need to have a declaration of the function, right. In this case, because I have defined the function before I used it, things are okay, right. I do not need to have a separate header file, those are things we will look at later, but I also do not need to have a separate declaration of a function. Now what does print info do? It takes a struct fruit x as input, right, and you will notice that just like I would say int x, I am actually saying struct fruit x. I am being explicit about exactly what I want it to do, right. And what it does is it basically prints out what I had earlier, right. It basically takes, there are %d of type %s costing %f each, and it takes x dot quantity, x dot name and x dot price. X, in other words, is now the parameter that has gone into the function, right. Does this work? Yeah, sure enough, it prints out exactly what we wanted, right. So this has made things a lot easier, right. I can just basically call print info of apples, print info bananas and so on, right. So let's try this for example with bananas, right. I could just call exactly the same thing, print underscore info and bananas, and this should also run fine. Yeah, it is able to print out that there are 20 of type bananas, okay. But now I have also got another function out here, right, just to sort of illustrate a point. Before we get to that function, one thing you need to understand is how do parameters get passed into functions, right. So for example, if I had int x declared out here, what would have happened is from the parent function, that is struct func, I would create a new stack frame, right, to call this new function print underscore info. I would copy the parameters to my function, that is x, into the stack frame corresponding to that new function, and then jump, right, or branch, basically start executing code at the new place, right, which means that the entire parameter, if it was an int, it is basically 4 bytes, needs to get copied into the stack frame. Now what happens with a struct? It turns out the entire struct needs to get copied, right, because what C does is uses something called passing by value. When you have a parameter to a function, it takes the value of the parameter and it actually copies the entire value into the stack frame of the function being called, so that the function has a copy of the value that it is working with. There are other programming languages and other ways of writing code, right, including for example in C++ there are something called references which allow you to pass by reference, meaning that instead of making a complete copy of the struct, you would just sort of pass something like a reference. The simplest way to think about it is like a pointer to the struct, and implicitly, right, the code over there would know that it needs to make it need not sort of make a complete copy of the struct, it just needs to pass a pointer to the struct, okay. Now C does not allow that, C only allows you to pass by value, right. Now why is that a problem? We have already seen an example of a struct that takes 32 bytes to store all its elements, and it is quite conceivable that you could easily have a struct that has potentially even hundreds of bytes. Think of a struct where one of the parameters, for example, is a character array where I have actually declared the character array as part of the struct, right. There is nothing preventing me from doing that. Previously of course I used a char star, but I could also have directly declared a character array inside a struct. And once you have things of that sort, it's quite easy to start imagining structs that can take hundreds of bytes in size. Passing a struct like that by value, right, when all that I need is to sort of print out the contents over there, is actually quite wasteful. It means that hundreds of bytes need to get copied from one place into another and then pretty much just printed and discarded. I could just as well have referred to the original place, printed the values from there. Okay. So, the alternative that C provides, right, is that you can actually pass a pointer to a struct. What that means is you have to take the responsibility of finding the pointer, use the ampersand operator to get the address and feed that in. That gets copied by value. In other words, the value of the pointer actually gets copied into the function, but the value of the pointer is always a fixed size, right. So, how does this work? Inside the parameter, I can use the notation star x, dereference the pointer. Now I have a struct fruit, and then I can use dot quantity, right. So, star x dot quantity, star x dot name, star x dot price would give me the exact value that I have. The position of these brackets out here is somewhat important, right, because if I try taking star x dot quantity, right, I can potentially try to dereference x dot quantity taken as an integer being treated as a pointer, right. So, just to avoid any possible confusion out there, what we usually do is give star x within parenthesis and then give the dot quantity. Now, this is such a common occurrence that there is also another shortcut that is provided by C, which is basically the arrow notation, right, which basically says x dash greater than, looks like an arrow pointing to the right, x arrow name has exactly the same meaning as star x dot name, right. So, where I have star x dot quantity, I could have given x arrow quantity, where I have x arrow name, I could have given star x dot name, they would have behaved exactly the same. The important point is I am now dealing with a pointer to a struct, I am dereferencing the pointer and then picking up one of the fields inside it. Does that work? Sure enough, right, I can just call print pointer info. But now notice that instead of just passing bananas, I have to actually take the pointer, ampersand bananas, right, that is the only thing. And once you run it, yes, it works exactly the same as before. Okay. So, this is a nice notation that is helpful when we want to sort of pass structs which could potentially be large in size into functions. Now, let us look at another example where we look at how to assign values from one struct to another. And just to sort of make a point over here, I am going to do something which is basically redeclare this struct fruit. You remember that struct fruit has already been declared as a global variable, right. Now, what ends up happening over here is, yeah, it is complaining because of something else. Let me just, yeah, I have this out here. So, it allows me to basically define a struct fruit and I can declare struct fruit apples out here. But you will notice that something's gone wrong. When I come to this print info, right, it basically seems to be indicating an error and I can try compiling it and it basically says there's an error, right. Now, what's the error? Passing struct fruit to parameter of incompatible type struct fruit. An example of a truly informative message from the C compiler. And yes, I am being sarcastic over there, right. You can imagine why it would be confusing to say that passing struct fruit to incompatible type struct fruit, they are exactly the same name. So, what is the difference out here, right? What has happened is the print info, right, over here is taking a struct fruit x, but which struct fruit was it? It is the one that was declared globally out here on line 3. Because that is the only struct fruit which print info knows about, right. When I declare the print info function, that is the struct fruit which is in scope. It turns out that when I go into this new function struct assign and declare another struct fruit, this has a different scope. It is limited to the scope of what is there inside this particular function. So, when I call print info with apples even though apples has been declared as struct fruit etc., and everything assigned properly, it has the same set of parameters, same names, everything looks identical about it. As far as the compiler is concerned, these are two different types. One was declared here on line 84, the one that printinfo expects to see was declared up there on line 3. Even though they have the same name, the compiler thinks they are different. Remember, when you declare a new variable, the old variable with the same name, right, it might be a global, gets shadowed. It's no longer visible in that scope. That's what's happening out here, right? Because the struct fruit has the same name, it ends up shadowing something that was already declared globally. This error message could probably have been a bit more clear, right, basically saying that you did some kind of shadowing, you have declared a new data type or something like that, but bottom line is this is what it means, right. Okay, the solution obviously is simple. I should not have redeclared a struct fruit in the first place, so let me just comment that out, and sure enough the warning goes away, right, the error goes away, and I am able to print info, right, and it says there are 10 of type apple etc. So print info, in other words, works. Okay, can I do this, which is basically declare a new struct fruit bananas equals apples and try printing that out? And yes, it worked, and what has happened over here is when I gave print info bananas, it seems to have printed exactly the same thing that was there inside apple. That is exactly what I expect, right? After all, I took the apple struct and assigned it into bananas. But now I could also go ahead and change something out here, right, bananas.name and bananas.quantity, right, and when I run this, I have a whole new element out here. But look at it, what has happened is I changed the name banana, that got updated, I changed the quantity to 30, the price remained the same, right. So this is in some sense one way by which I can create one basic value, start assigning it or make copies of it, and then update only the parts that I need. Okay. Now you will remember that I had mentioned that comparison is not really possible. The only thing that I can really show over here is that the moment I try comparing apples and bananas, it basically says invalid expression. Of course, I should probably have tried comparing apples and oranges, right, but apples and bananas are also not comparable, as you can see. So you cannot do this. If you do want to compare this, you would have to write another function that takes two struct fruits as input, iterates over each of the individual parameters present inside, right, the name, the quantity, the price, checks whether they are equal, and then finally returns true or false, well 0 or 1, right, essentially to indicate whether something is valid or not, because C does not have a true Boolean data type, but we can sort of emulate it using integers. So I will have to comment this out because it is a compiler error. I cannot even like leave the code in there and proceed. Now let us get rid of some of these prints. Now this is an example just to show you what it looks like in order to create what is called a deep copy, right. What I mean by a deep copy is I am declaring a new data type struct dummy, right, which has a char a and an int b of 4, it is in other words an array of 4 elements, okay, and I am sort of assigning it straight away out here. I basically assign it to this character so that the element a over here gets the value capital A, it gets the character capital A, and then I have the string out here which basically, or rather this array of integers which has got this out here, right, and I should find that when I print x dot a, I find this value over here and so on, right. Yeah. Now what I am doing is I am making a copy, I am declaring a new struct dummy y, making a copy of it, and now going ahead and changing the values y dot b of I. Okay. Now here is where things get a little potentially confusing, because is this int b a pointer or is it a fixed array, right? And the reason why I asked that question is, if it was a pointer, then this copy out here that y made of x should just have copied the pointer and not the individual values. But it turns out that when you actually declare something as int b of 4 like this, it actually goes ahead and makes a full copy of the array, right. So, the entire b of 4 is taken as a data type, the 4 elements out there are copied. So, then what happens is, even if I go and change y dot b, it does not affect x dot b. Okay. We can take a look at how that happens. You can see that after when I printf this %c, I find that it actually shows the value a out there, but this printf shows that x dot b has the values 1, 2, 3, 4, which is what I initialized it, but y dot b has changed to 0, 1, 4 and 9, which is I into I as seen over here, right. So, in other words, changing the value of y dot b did not have any effect on the values of x dot b, right. Now, in order to truly understand why this is or is not a problem, we actually need to understand something about dynamic memory allocation. So, for the time being, I am going to leave that out. When we get to dynamic memory allocation, I will show an example of how when you copy structs, you could potentially end up with a problem that you end up pointing to the same location and you can end up messing up data that you did not expect to. There is one sort of interesting use case of pointers and that I had not mentioned earlier, which is basically a pointer to a function, right. We know that we can get pointers to integers, you can get pointers to floats, you can get pointers to characters and so on, or a character array. What does a pointer to a function mean? Now, when you think about the fact that a function is basically code which is a set of machine instructions that are stored somewhere in the memory of the system, then it starts to make sense to think of a pointer to a function, because after all that code starts at some place in the memory and that starting location is an address in memory, right. It turns out that you can actually take pointers to functions, and by storing pointers to functions inside structs, you can sort of get to the point where we are almost getting to a kind of behavior which starts to emulate something like object oriented programming. An example of that is shown over here. This is a slightly more advanced use of pointers as well as structs, right. It is worth knowing because it is something that you might encounter at some point when you write C code, but it is probably not something you arbitrarily want to make use of over here, right. If you do really want to do object oriented programming, there are languages that are better suited to it, right. So, fine, let us look at this particular struct definition out here, which is basically a struct animal. It has a char star name, and now on line 144 you can see that it has what is called void star speak and parenthesis out here, right. This notation is basically telling us that speak is a pointer to a function. It is basically a sort of void star pointer, but because of the parenthesis out here, it is a pointer to a function. It does not tell you what the function returns, right, nothing else about it. It basically tells you that this is a pointer to a function. And what I can store in speak, in other words, right, is pointers to functions. What does that mean? It means that I can now start assigning things. Cat.name equals cat. This is easy to understand. I have basically created this string somewhere in the constant memory of the program and assigned the pointer to that into cat.name, which is char star, okay. And dog.name is equal to dog also makes sense. But now look at cat.speak. I have given the word meow. Notice that there are no quotes over here. So, what is meow? It turns out it is a function that I have declared up here on, that I have defined up here on line 138, right. It basically just prints out the word meow, right, but what it does not matter. The point is that it is being defined as a function, which means that I can actually use it, right. I have just given the word meow, there are no parentheses after it. In other words, I am not calling the function. If I had given parentheses after meow, that would mean that I am actually calling the function meow. I am not. I am only taking the name of that function, or in other words, the pointer to the function, and assigning it to cat.speak. Similarly, I am taking the pointer to bark and assigning the dog.speak. And what that means is I can now call cat.speak notice the parenthesis out here, right? I am actually calling the function. And when I do dog.speak again with parenthesis, I am calling the function dog.speak. What happens when I run this? Pretty much as expected, cat.speak printed out meow and dog.speak printed bark, right? So pointers to functions exist, right? After all, a function is some code sitting somewhere in memory. You can get the address of that code, that's a pointer to the function. By having that pointer to the function somewhere inside a struct, you are associating that function with that particular element. So in other words, I have managed to say that the particular element cat speaks by saying meow. This is in some sense the essence of one of those parts of object oriented programming, where a similar kind of object, right, a structure, can have different behaviors depending on how it is called or how it is invoked, right. So it is possible to have multiple different kinds of functions that get called depending on certain parameters of the structure itself. So this is in some sense how object oriented programming also works, right. Ultimately it maintains a lookup table of different kinds of methods corresponding to a given object. All of them are function pointers and are associated with a struct, a structured data type, which stores information about that particular object, right. C does not by its very nature have a notion of object oriented programming. This is a way by which you can sort of emulate a behavior of object oriented programming. It is not really advisable unless you are very clear, unless it really makes a difference to how you are going to write your code. Because in most cases people reading C code are not expecting to see things like this. If you want object oriented programming, there are other languages that are much better at it, right. So although this exists, it is probably better off to stick to reasonably straightforward and easy to understand functions, right, which actually take the exact struct that you want and perform the behavior that you need.